Everything around you, this desk, the air you breathe, even you, is made of something almost impossibly small. Welcome to Chapter 3, Atoms and Molecules, the Building Blocks of All Matter. In this chapter, we will uncover the laws that govern how matter combines, meet the genius of John Dalton, and understand what atoms and molecules actually are. We will also explore the mole concept, a chemist's secret weapon for counting particles too tiny to see. By the end, you will see the world differently, because once you know about atoms, you can never unsee them. Before we talk about atoms, we need two laws that all chemical reactions must obey. These laws were discovered by careful experiments long before anyone could actually see an atom. The first is Lavoisier's law of conservation of mass. In any chemical reaction, the total mass of the reactants always equals the total mass of the products. Mass is never created and never destroyed. Think of it like a recipe. You start with 3 grams of hydrogen and 24 grams of oxygen. After the reaction, you get exactly 27 grams of water. Not a single atom is lost. The second law is Proust's law of constant proportions. No matter where you get water from, a river, a cloud, a laboratory, it always contains hydrogen and oxygen in the same fixed mass ratio, 1:8. This means elements always combine in fixed whole number mass ratios. The composition of a pure compound is constant, regardless of its source or how it was made. In the real world, these laws are the backbone of industrial chemistry. Factories use the law of conservation of mass to calculate exact raw material quantities, making sure no expensive reactant goes to waste. In 1808, John Dalton proposed a bold theory that tried to explain why those two laws always hold. He called it the atomic theory, and it changed chemistry forever. Postulate 1. All matter is made up of tiny, indivisible particles called atoms. The word atom comes from the Greek word atomos, meaning uncuttable. Postulate 2. Atoms of the same element are identical in mass and properties, but atoms of different elements are different from each other. Postulate 3. Atoms combine in simple whole number ratios to form compounds. No fractions, no decimals, always clean whole numbers. Postulate 4. Atoms cannot be created or destroyed in a chemical reaction. They are simply rearranged. This directly explains why mass is always conserved. And because atoms always combine in fixed whole number ratios, the mass ratio of elements in a compound is always constant. That explains the law of constant proportions too. Dalton's theory was a triumph. For the first time, chemistry had a microscopic explanation for macroscopic observations. But as we'll see shortly, it wasn't perfect. Dalton's theory was groundbreaking, but science moves forward. In the 19th and 20th centuries, new discoveries revealed that the theory had some important gaps. Limitation 1. Dalton said atoms are indivisible. But we now know that atoms are made of even smaller particles, protons, neutrons, and electrons. Limitation 2. Dalton said all atoms of the same element are identical, but isotopes prove otherwise. Carbon-12 and carbon-14 are both carbon, yet they have different masses. Limitation 3. Dalton implied atoms of the same element don't bond with each other, but molecules like oxygen gas, O2, are made of two identical oxygen atoms bonded together. So that's not true either. Despite these limitations, Dalton's core idea that matter is made of atoms that combine in fixed ratios remains the foundation of modern chemistry. So what exactly is an atom? An atom is the smallest particle of an element that still retains the chemical identity of that element. If you break an oxygen atom apart into protons and electrons, those pieces are no longer oxygen, they have no chemical identity. The atom is the smallest unit that still is the element. Here's something surprising. Most atoms cannot exist independently. Hydrogen atoms, oxygen atoms, they don't float around alone in nature. They immediately bond with other atoms to form molecules. Noble gases like helium and argon are exceptions. They are stable as single atoms, what we call monoatomic. They don't need to bond because their outer electron shells are already full. Just how small is an atom? If you lined up 100 million hydrogen atoms side by side, they would stretch only about 1 centimeter. Atoms are almost unimaginably tiny. Atoms are so tiny that measuring their mass in grams gives us impossibly small numbers like 1 times 10 to the power minus 24 grams. That's not practical. So chemists invented a better unit. One atomic mass unit, or AMU, is defined as exactly 1/12 the mass of one carbon-12 atom. Carbon-12 was chosen as the international reference standard. Using this scale, a hydrogen atom has a mass of about 1 AMU, an oxygen atom is about 16 AMU, a carbon atom is exactly 12 AMU by definition. This is called the relative atomic mass. It tells us how heavy an atom is relative to the carbon-12 standard. It has no units, just a pure number. Notice that chlorine has a mass of 35.5, not a whole number. That's because natural chlorine is a mixture of isotopes, mostly Cl35 and some Cl37. The atomic mass is a weighted average. We said atoms often can't exist alone, so what do they form? They form molecules. A molecule is the smallest particle of an element or compound that can exist independently and still show the properties of that substance. A molecule is formed when two or more atoms are held together by chemical bonds. Those bonds can be between atoms of the same element or atoms of different elements. The key difference between an atom and a molecule: an atom is the smallest unit of an element, while a molecule is the smallest unit that can exist on its own in a free state. In the real world, when you breathe in oxygen, you're not breathing individual O atoms, you're breathing O2 molecules. The diatomic molecule is the form in which oxygen naturally exists in air. Molecules of elements: molecules made from only one type of element can be grouped into three categories based on how many atoms they contain. Monoatomic molecules have just one atom. These are the noble gases: helium, neon, argon. They're so stable they never need to bond with anything. Diatomic molecules have exactly two atoms of the same element bonded together. The most important ones are hydrogen, oxygen, nitrogen, and chlorine, all gases at room temperature. Polyatomic molecules contain more than two atoms of the same element. White phosphorus is P4, four phosphorus atoms in a tetrahedron. Sulfur is S8, eight sulfur atoms in a ring. Here's a useful mnemonic for remembering the diatomic elements: Hofbrinklö, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. These seven elements always exist as diatomic molecules in their elemental form. When atoms of different elements bond together, they form molecules of compounds. Unlike element molecules, these contain more than one type of atom. Water, H2O2 hydrogen atoms bonded to one oxygen atom. The subscript 2 in H2O tells us there are two hydrogen atoms. There's no subscript after O, which means just one oxygen atom. Carbon dioxide, CO2, one carbon atom bonded to two oxygen atoms. This is the gas you exhale with every breath. Carbon is gray, oxygen is red. Remember our color code. The chemical formula of a compound is its most compact description. It tells you exactly which elements are present and in what numerical ratio of atoms. A real-world connection: carbon dioxide is produced in your cells during cellular respiration, and it's also a key greenhouse gas in our atmosphere. One simple formula, CO2, represents enormous chemical significance. A chemical formula is a symbolic shorthand that tells us which elements are in a compound and how many atoms of each are present. Learning to read and write formulas is a core chemistry skill. To write a formula, we use the valency of each element. Valency is the combining capacity of an atom, how many bonds it can form. Magnesium has valency 2 and oxygen has valency 2. Now we use the criss-cross method. The valency of each element becomes the subscript of the other. Magnesium's valency 2 crosses over to become oxygen subscript, and oxygen's valency 2 crosses over to magnesium subscript. Let's try aluminum chloride. Aluminum has valency 3, chlorine has valency 1. Cross them over, chlorine gets subscript 3, aluminum gets subscript 1, which we don't write. Result AlCl3. When a polyatomic ion like phosphate PO4 with charge 3 minus appears more than once, we put it in brackets. Calcium has valency 2, phosphate has valency 3. Cross them over to get Ca3 PO4 2. Chemical formulas are used everywhere in medicine, nutrition labels, environmental reports. When you see NaCl on a salt packet, that's the formula for sodium chloride, one sodium atom bonded to one chlorine atom. Not all particles in chemistry are neutral molecules. When an atom gains or loses electrons, it becomes electrically charged. We call these charged particles ions. When an atom loses electrons, it becomes positively charged. We call it a cation. Common cations include sodium Na+, calcium Ca2+, and ammonium NH4+. When an atom gains electrons, it becomes negatively charged. We call it an anion. Common anions include chloride Cl-, oxide O2-, and sulfate SO4 2-. Polyatomic ions are groups of atoms that carry a charge together. Sulfate SO4 2-, carbonate CO3 2-, nitrate NO3-, and ammonium NH4+ are the most common ones you'll encounter. When writing formulas for ionic compounds, the total positive charge must equal the total negative charge. Sodium chloride, Na+ and Cl- charges cancel. Formula is NaCl. Calcium chloride, Ca2+ and Cl-. You need 2 chloride ions to balance the 2+ charge, giving CaCl2. Ions are central to so much of life and industry. Your nerve cells fire because of sodium and potassium ions moving across membranes. Sports drinks replenish these same ions lost in sweat. The molecular mass of a compound is simply the sum of the atomic masses of all the atoms present in one molecule. Let's learn to calculate it step by step. Water, H2O, there are 2 hydrogen atoms and 1 oxygen atom. 2 times 1 plus 1 times 16 equals 18. The molecular mass of water is 18 AMU. Carbon dioxide, CO2, 1 carbon plus 2 oxygen atoms. 12 plus 32 equals 44. The molecular mass of CO2 is 44 AMU. Sulfuric acid, H2SO4, 2 hydrogen, 1 sulfur, 4 oxygen. That's 2 plus 32 plus 64, which equals 98 AMU. Calcium hydroxide, CaOH2, 1 calcium. But the OH group appears twice, giving 2 oxygen and 2 hydrogen. So 40 plus 32 plus 2 equals 74 AMU. Molecular mass calculations are used in the pharmaceutical industry to determine exact dosages. A drug molecule's molecular mass tells chemists how much of it makes 1 mole, crucial for accurate medicine manufacturing. For ionic compounds like sodium chloride, we can't really talk about a molecule because the structure is a giant continuous lattice, not individual molecules, so instead we use the term formula unit. The formula unit mass is calculated exactly the same way as molecular mass. Sum the atomic masses of all atoms in the formula. For NaCl, sodium is 23, chlorine is 35.5, total is 58.5 AMU. Let's calculate for magnesium chloride, MgCl2. Magnesium has mass 24, chlorine is 35.5, and there are 2 chlorine atoms. So 24 plus 71 equals 95 AMU. The name is different, formula unit mass instead of molecular mass, but the calculation is identical. The important thing is understanding when to use each term. Atoms are far too small to count individually. If you tried to count the atoms in a single grain of sand one by one, it would take longer than the age of the universe. Chemists needed a smarter way to count. We already use group counting in everyday life. A dozen means 12 items. A gross means 144 items. For atoms, chemists use a much larger group called the mole. 1 mole equals 6.022 times 10 to the power 23 particles. This number is called Avogadro's number, named after the Italian scientist Amedeo Avogadro. The mole is the bridge between the microscopic world of atoms and the macroscopic world of the laboratory. We can't weigh individual atoms, but we can weigh 1 mole of them on a balance. So when a chemist says I have 1 mole of water, they mean they have 6.022 times 10 to the 23 water molecules, which happens to weigh 18 grams. One number connects counting to weighing. We now know that 1 mole of any substance contains Avogadro's number of particles. But how much does 1 mole weigh? That's what molar mass tells us. Here's the beautiful shortcut. The molar mass in grams per mole is numerically the same as the atomic or molecular mass in AMU. Carbon's atomic mass is 12 AMU, so its molar mass is 12 grams per mole. So for hydrogen, molar mass is 2 grams per mole. Since H2 has molecular mass 2 AMU, for oxygen gas O2 it's 32 grams per mole, for water 18 grams per mole. Now let's use molar mass to convert. To find the mass of a given number of moles, multiply moles by molar mass. To find moles from a given mass, divide mass by molar mass. Example, how many grams are in 3 moles of water? Multiply 3 moles by 18 grams per mole. Answer, 54 grams. Example, how many moles is 44 grams of carbon dioxide? Divide 44 by 44 grams per mole. Answer, exactly 1 mole. Molar mass is used constantly in real chemistry labs and industry. Every time a pharmaceutical company makes a batch of medicine, they use molar mass calculations to ensure exactly the right number of molecules goes into each tablet. And that, my friends, is the incredible world of atoms and molecules. Everything you touch, taste, breathe, and see is made of these tiny invisible building blocks. From Dalton's atomic theory to the mole concept, you've just built the foundation of all chemistry. Give yourself some credit. This is big stuff. If this video helped you understand even one concept more clearly, smash that like button right now. It genuinely helps this channel grow. Got a question? Confused about valency, moles or ions? Drop it in the comments below. I read every single one and I'd love to help you out. Know a classmate who's struggling with chemistry? Share this video with them. One share from you could save their exam grade. And if you haven't subscribed yet, what are you waiting for? Hit that subscribe button and the bell icon so you never miss a new lesson. Thank you so much for watching all the way to the end. That means the world to me. Keep questioning, keep learning, and I'll see you in the next one.